Ions and ionic compounds. Now, first off, ions come from transfer of electrons. All right, either atoms are gaining electrons or they're losing electrons. That's what it means to transfer. And so we can take a look at something like a sodium atom. Now, sodium is element number 11 if you look on the periodic table, which means it has 11 protons, which are positive. And a neutral atom of sodium also has 11 electrons, which are negative. And so if we add 11 and negative 11, we get an overall charge of 0, which means it's neutral. Okay, now, sodium likes to lose an electron. If it's in a compound, it would like to lose 1 electron. And so if we take that same sodium and we lose an electron, we now have 10 electrons. But since it's still sodium, and what makes sodium sodium is that sodium has 11 protons. All sodiums have 11 protons. And so now if we say 11 minus 10, we get a positive 1 charge. And we say that that sodium now has a plus 1 charge. Now, we usually don't put a 1 up there. We just put the plus. And other atoms are going to have other charges, so maybe it's plus 2, plus 3, plus whatever. But sodium likes to have a plus 1 charge. Chlorine, for instance, as well, when it becomes an ion, it wants to have a minus 1 charge. But it starts out with 17 protons and 17 electrons. And neutral chlorine has 17 electrons. Now chlorine likes to have an extra electron. It really wants to have 1 more electron. So if it picks up 1 more electron, it now has 18 electrons total. But since it's chlorine, it still has 17 protons. And so we write its symbol as chlorine, and we'll go ahead and subtract the 18 from the 17, and so we write that as chlorine minus. And so we can do the same thing with any ion. Now, I'm just showing you where the charge comes from. It's because you either have extra electrons compared to the protons, or you're missing electrons compared to the protons. Now, from here on out, we don't care how many protons we have. The only time we really care about the number of protons is when we were doing the nuclear chemistry part, where we were changing the number of protons, potentially number of neutrons, and we didn't care about the electrons then. Now, all we care about is the electrons from here on out. Okay, now, we need to be able to predict what the charge is going to be if an atom becomes an ion. What is the charge going to be? And it turns out that the periodic table can help us decide what the charge is going to be. And there's a pattern. And that's the wonderful thing about the periodic table, is there's a lot of information and there's patterns that you can use. And it turns out the patterns depend upon the group. A group being a column up and down, that's a group. And so group 1, 1A, well, they are always plus 1. And group 2 is always plus 2. And we jump across, don't worry about the transition elements in the middle for right now. But we're going over to boron and aluminum in group 3A, and those guys, that group is always plus 3. And we skip over carbon. Carbon can have several different charges. And we go over to nitrogen, and we change sign, and it becomes minus 3 for everything down below nitrogen. Oxygen and everything below is minus 2. Fluorine and everyone below is minus 1. And the noble gases, they don't form charges at all. And so everyone, and I can't emphasize this enough, if you look over at oxygen, when it becomes an ion, it's always -2. And if you look below at sulfur, it's always -2, and so forth on down the line, that when they become ions, those are the charges that they will usually take. And we'll just go ahead and say that for our purposes, we're going to assume, unless we figure out otherwise, that those charges are always what they are: +1, +2, +3, -3, -2, -1, and 0. Now, the elements in the middle, though, the transition elements, they have more than one charge. Okay, and for those, we don't know ahead of time what the charges are going to be, and you don't have to memorize what the charges are on the periodic table. But on the periodic table, for instance, iron is +2 or +3, and cobalt's +2 or +3, and nickel's +2 or +3. But then we get to copper, it can be +1 or +2. And zinc is always +2, cadmium's always +2, and silver's always +1. So just to make it even more confusing, the transition elements can have more than one charge, and 3 of them actually have only one possible charge. Okay, more on that in a little bit. For right now, let's focus on the +1, +2, +3, -3, -2, -1, 0 pattern that we know is going to be the case. Okay, and I'll show you later on how we can figure out what the charge is on these transition metals. All right, so if we look at this, we can see there's a pattern, and the way I like to see the pattern is like this. I like to think of it as kind of climbing up and climbing down, and so we have 1 plus, 2 plus, 3 plus, 3 minus, 2 minus, 1 minus. That's how I like to think about it. This is, we're climbing up, we're climbing down. And you just need to know that that they correspond in order with the groups as you go across the periodic table. So we can look at our periodic table, and I can tell you, just by looking at the periodic table, what the charge is on that element. And so if I was to say, what's the charge on calcium, what would we say? Well, we would look at the periodic table. Let's go back to the periodic table. We find calcium. There's calcium over here. And we see it's in the +2 column. And so we go back to our calcium and we say, well, that's 2 plus. What if we were to say, let's say, what's the charge on a fluorine? And we go back to our periodic table and we take a look and we try to find fluorine. And we see that fluorine is in the -1 column, in the -1 group. And we go back to our element and we say, well, that's F minus. Now, usually we don't put a 1 up there because if there's a charge, we're assuming that we have at least one of them. Okay, and we can do that for any element. I mean, any of the elements, the common ones that fall underneath those columns, and we look for aluminum and we see it's in the 3 plus column. And here it is. It's in the 3 plus column. And so this is very handy, that as long as you have a periodic table in front of you, and you do, you have the charge of whatever it is. Oxygen's 2 minus. Sulfur below oxygen is also 2 minus, and so forth. So having a periodic table in front of you, you can decide what the charge is going to be, because it follows that pattern: +1, +2, +3, -3, -2, -1, and so forth. Now, you may have noticed that I have put the 2 on the calcium in front of the plus instead of saying +2. What if I was to say calcium +2? Is that wrong? And the answer is no, not really. Just try to be consistent. Sometimes I kind of flip back and forth, but generally, when I say, if I have a number, if I put a plus or a minus in front of that number, to me this looks like something I measured. Okay, like plus 2.1. Okay, that's just some number. Okay, but if I have something that's got like a 2 in front of the plus, to me that's saying I have 2 plus charges, or that I am missing 2 electrons. Now, electrons are counted. They're not measured out in half electrons or 0.1 electrons. So that's generally why I prefer, when I'm putting down charges, I prefer to put the charge behind the number. Because to me, that looks more like a counted number, because we're counting how many electrons we're missing, how many electrons extra we have. So let's recap here. What does it mean when we say 2 plus? 2 plus means we're missing 2 electrons. We have 2 less electrons. The F minus, well, it has 1 extra electron because electrons are negative. And aluminum 3 plus means we're missing 3 electrons. And the oxygen 2 minus means we have 2 extra electrons. And the sulfur 2 minus means we also have 2 extra electrons. Okay? So why do we have missing or extra electrons, and why does it follow that pattern on the periodic table? And what's going on is this right here. We have something called the octet rule. All right? And it says atoms lose, gain, or share electrons to have a full shell. Now notice, when we say this, it's not to get 8 electrons. It's not to get 8. Even though the octet rule means 8. Now, it was originally named 8 because it was assumed, the octet rule, it was assumed that all atoms want to have 8 electrons on what's called the valence shell. And that's mostly true, but not completely true. What we're trying to do is get what's called a full shell. And just to draw you what I mean by full shell, atoms fill up with electrons in these orbitals and energy levels. And when you complete one energy level, which is a shell, you build another shell, and you build another shell. And this outermost shell, the outermost electrons, are called valence electrons. They're the electrons that are on the outside. And generally what you're going to do is you're going to gain or lose electrons to get a full shell, which is a full valence electrons for that shell. Now, if we go back to our periodic table, and let me go ahead and erase all this here, okay? Let's just go ahead and take a moment, clean up my periodic table. Of course, I could have just closed it and reopened it. And maybe I'll do that next time. But what we have here is a periodic table. Now remember these charges. I shouldn't have erased those. That's okay. We can fix that. And we look at this periodic table. Now where is a full shell? Well, a full shell is any time we complete a row. Those are the noble gases. That's where the full shell is. And if you remember, when we had plus 1, plus 2, plus 3, minus 3, minus 2, minus 1, and we said, these are missing electrons, or these are extra electrons. And I said the octet rule says you're gaining or losing or sharing electrons to get a full shell. Well, what does that mean? Well, let's take a look at fluorine. And you look at fluorine on your periodic table, that's element F on the right-hand side, and you see it has element 9. Now, we already decided that when fluorine forms an ion, it goes to 1 minus because it has 1 extra electron. Well, if it's element number 9, you started out with 9 electrons. And if you add one more electron, what do you get? You get 10 electrons, just like neon. See, if you have the same number of electrons as the noble gas, then that means that you have a full shell. That's what it means. You've reached the end of the row, the end of the period. And so fluorine, when it gains an electron, it now has 10 electrons. It goes from 9 to 10. And similarly for oxygen. Oxygen starts out with 8 electrons. Minus 2 means what? That you have 2 extra electrons. Well, 8 plus 2 gives you what? What does 8 plus 2 give you? Gives you 10 again. And the same thing with nitrogen. If you add 3, what do you get? You get 7 plus 3. That gets you 10. Now, the plus elements, well, it's the same situation. You're gaining or losing electrons. In this case, for the plus elements, you're losing electrons because that's what it means to be plus 3 or plus 2 or plus 1, is you have lost electrons. So let's take a look at, say one of my favorite elements. Let's take a look at calcium. Calcium's right here on the far left-hand side. Let me cover up that 20. Here it is on the far left-hand side, and you start with 20 electrons. Well, if you have a plus 2 and calcium is plus 2, that means you've lost 2 electrons. So and you start out with 20, calcium's element number 20, you start out with 20 electrons and you lose 2. Well, what does that give you? Well, 20 minus 2 gives you 18. You see that? It's the previous row. It's the previous shell, and that's okay. All we're looking for is a completed shell, and it doesn't matter that you had to go to the previous row, because that is the last filled shell, was where argon was with 18 electrons. And we can do the same thing with say, potassium. Potassium has its element number 19. It's element K over here on the far left-hand side. And it becomes plus 1 when it becomes an ion. And so 19 minus 1, because if it's plus 1, that means you've lost an electron. So 19 minus 1 gives you what? You're back to 18 with argon. So that's how the octet rules work. And now this is why we don't consider it, gaining or losing to get 8, because let's take a look at lithium. If you look at lithium, lithium has 3 electrons to start out with. It becomes Li plus or lithium plus when it becomes an ion. But look, you start with 3. 3 minus 1 gives you 2. That's helium. And 2's not 8. 2 is not 8. So that's the kind of thing that when we look at the octet rule, we can't say, well, gains and losers are shares to have 8 electrons, even though the octet rule does say 8. Okay, so that's the octet rule. Now, one more thing, we have to have 2 definitions here, and that is when we do have ions, they have a name, a generic name. And when we have something, we have these things called, well, they're ions, which means they have a net charge of something, net charge positive or negative. And the positive ions we call cations. It's not pronounced cations, it's pronounced cation, like a cat and an ion. Cations are positive. And they're usually metals. That's another reason why you need to know where your metals are on your periodic table. And cations are usually positive. And the way that we're going to remember the definition of a cation is if you look in the word cation, and I drew that T like a plus, it looks like a plus. So cations are positive, and that would be things like calcium 2 plus, aluminum 3 plus, and so forth. And we have another kind of ion, and we call them anions. And, well, what's the opposite of a positive? Well, that's a negative. So anions are negative. And usually they're nonmetals. And those are the elements that are up in the upper right-hand corner. And the way we're going to remember anion is in the word itself. And this was pointed out to me by someone some years ago. And you can say a negative ion. Do you see that? A negative ion. It's in the word. A negative ion. Anion. Okay? Now, just to remind you where the metals and non-metals are, everything to the left of that yellow ziggy line, that yellow zigzag staircase is a metal. And everything up and to the right is a non-metal. Okay, everything up and to the right is a non-metal. Everything to the left and down of that staircase is a metal. And don't worry about the metalloids. That's a little bit more later on. They have a tendency to form what are called covalent compounds, more so than, say, ionic compounds. Okay, so those are our anions and cations, and this is how we're going to remember how they're named. Okay, so ions have a net positive or negative charge, and we're either gaining or losing electrons to get full valence shells. Now, our final skill before we get to making ionic compounds is we have to be able to figure out how many valence electrons does an element have. And so we say valence electrons. Okay. So we're gaining or losing valence electrons, and those, as I mentioned before, are the outermost electrons. Those are the things that are going to do all the interesting stuff in chemistry, or the valence electrons, the outermost electrons. And our final skill is how to find how many. How many? Well, that's equal to the group number. Not the 1 through 18, but like the 1A, 2A, etc., all the way over to 8A, if you look on your periodic chart. And so we go through 1 through 8A, which means we have a maximum of 8 valence electrons. And it is not the same as total. Do not be that person that says, oh yeah, chlorine, it has element number 17, it must have 17 valence electrons. No. The valence electrons are the outermost electrons. There's electrons that are inside the valence shell, and those are called core electrons. So the core electrons are the inside electrons. They are inside the valence shell. And we don't worry about the core electrons because generally other elements can't see the core electrons, C-O-R-E, core electrons. And so we're worried about the valence electrons. And so it's the same as the group number. Let me pull up the periodic table again. And so we look up here, and if you see, we have 1A, 2A, and just ignore these guys in the middle. Those are special. 3A, 4A, 5A, 6A, 7A, 8A. Okay? And the group numbers correspond to how many valence electrons that we have. And so we have 1, 2, 3, 4, 5, 6, 7, 8. And they're just counted. That's all we're doing. We're just counting. Not to be confused with the charges. What were the charges? The charges were +1, +2, +3, -3, -2, -1, 0. You see what I mean? The periodic table has a lot of patterns. The periodic table has a lot of information on it. And so the valence electrons are the same as the group number. So we can do things with this, like we can look at elements and we can say, well, what's the charge and how many valence electrons it has? And so we could say, well, what's the charge on aluminum? Well, we look on the periodic table and we see 3+, but how many valence electrons does aluminum have? And we look at our periodic table. Let me pull up another periodic table here. We look at our periodic table and we look across and we go 1, 2, 3. Oh, aluminum has 3 valence electrons. And it's just so happens to work out that it's not the same as the charge, though. And unfortunately, I picked that one first, valence electrons. Well, how about oxygen? Well, oxygen, it has a charge of 2 minus, but if we look on the periodic table, where's oxygen as far as valence electrons? And we go 1, 2, 3, 4, 5, 6, and we see it's in the 6th column. Everything under oxygen and below has a charge of 2 minus, but they have 6 valence electrons. And so we look and we say 6 valence electrons. And we go across and we say, well, how many does sodium have? Well, sodium has a +1 charge, and it's in the 1st column. If you look on your periodic table, it has 1 valence electron. And we can look at, say, fluorine. Fluorine's F minus. Means it has 1 extra electron, but it has 7 valence electrons. So there's 2 skills here that we should be able to do so far, and that is we should be able to look at our periodic table, and we should be able to say, well, what's the charge if it is an ion? It doesn't have to be an ion. It can be neutral. But if it has a charge, what's the charge going to be? And it's going to be +1, +2, +3, -3, -2, -1. And of course, 0 for the noble gases because they don't make bonds at all. And where did these numbers come from? They come from the octet rule, where we're going to lose, gain, share to get a full valence shell, and a full valence shell being the same as the noble gas on the far right-hand side, whether it's on the same row or the previous row. It doesn't matter. And so when we do that, we can also look at our periodic table and we can say, well, how many valence electrons do you have, those outermost electrons? And it follows the pattern. +1, +2, +3, plus it goes 1, 2, 3, 4, 5, 6, 7, 8, depending on where it is. Okay, so these are the essential skills for working with ions. Now, once we have ions, we can make something called an ionic compound. This is where it starts getting interesting. This has ions bonded together to make a compound. And very important, the net charge must equal 0. Net charge of any ionic compound must equal 0. In an ionic compound, you're going to have an anion with a cation. But understand, what's an anion? An anion is a minus charge, and a cation is a plus charge. And when you add them together, they have to equal 0. Okay, this is very, very important. And so we could make ionic compounds out of just pick some things at random. And let's start with our original 2 ions that we made, which was sodium and chlorine. Sodium, when it becomes an ion, it's in the 1st column, and so it's a +1 element. And when chlorine becomes an ion, it becomes minus because it's in the 7th column, where we have the -1 charge, following the pattern of +1, +2, +3, -3, -2, -1. By the way, we're done with valence electrons for the time being. And so if I put these together as a compound, then they come together like this. And that's it. Now, we don't put the charges on the elements once we put it together. In other words, you don't put in here, and I'm doing it in red because I don't want you to do it. You don't go plus and a minus in there. Okay, the charges are still there, though. That sodium is still a plus charged ion. The chlorine is still a plus charged ion, and it's electrostatic attraction that's holding them together. Just like if you rub a balloon on your head, you can get it to stick on the wall. That's because the electrons are being attracted to the positive charge on the balloon. Okay, And so they're together. Now, +1, now let's switch colors because I try to reserve red for don't do this. And so we have a +1 -1 equals 0. And so the net charge on that compound, and you may know it as ordinary salt or sodium chloride, the net charge on that compound is 0. Okay? And we can try some other ones. We can try some other ones where the charges are already equal. And so let's say we had calcium and oxygen. And I look on my periodic table and I find calcium, and we go +1, +2, +3, -3, -2, -1, and I see it's in the +2 range, and so I say 2 plus. And we look across following the pattern once again, and we see that oxygen is 2 minus. And if we go ahead and push these guys together to make a compound, an ionic compound, we see that it's a calcium with an oxygen, and we see that +2 -2 equals 0. And sure enough, it must equal 0. So we have ions bonded together to make a compound, and the net charge is always 0. It has to be 0. Now, what are we going to do if we have a situation where the charges are not equal? And so let's say we had aluminum with oxygen. And we look on the periodic table and we see that aluminum is 3 plus, and we see that oxygen is 2 minus. Now, if we go ahead and push these together, we would have the aluminum bonded to the oxygen, okay? But there's a problem here, because aluminum is 3 plus, and oxygen is -2, we get +1. This is bad. Okay, it's bad because ionic compounds must have a net charge of 0. So how are we going to fix this? So what we're going to do is we're going to do something called crossing charges. Now, we only do this when the charges are not equal. Whoops, let's change colors here. Now, when we cross charges, what we're doing is we're making sure that the total is going to be equal to 0, because that's what we have to have for any ionic compound. And so what we mean by crossing charges is whatever the charge is that we're going to cross it over to the other one. Now watch this. Now I'm crossing just the number, not the charge. Okay, I'm going to cross just the number over to the oxygen. There it is. And I'm going to take just the number off of the oxygen, not the minus part, not the minus. And we're going to cross it over to the aluminum. Okay. Now, when we have a subscript on this new compound, this means how many. The 2 and the 3 mean when they're subscript. That means off down to the right. This means how many. How many of the element or the atom, or whatever it is, because you can have subscript 3. We're going to get into that later, where we have things called polyatomic ions. And so it tells you how many. So this means that this compound here, and I'll tell you the name, it's aluminum oxide. It has 2 aluminums because the 2 goes with the previous thing. So we have 2 aluminums and we have 3 oxygens. Okay? Now the charges are still there, but we didn't put the charge up top. We don't put anything up here. All right, don't put anything up there. And make sure that 2 is down and to the right. Don't put it right next to the aluminum. The 3 is down to the right. Don't put it right next to the oxygen. It's a subscript. And so now I can tell you what was our goal here. Our goal here was to get the charges to add up to 0. So now I have 2 aluminums. And each aluminum has a +3 charge. And that equals +6. And I have 3 oxygens, and each one of those oxygens is -2. And that equals -6. Oh, look here. 6 minus 6 equals 0. And so sure enough, we're good. And we can do this with any pair of atoms with arbitrary charges on them. Well, we have to look on the periodic table, and we'll do a final example here across some charges, and that is, say, calcium with a nitrogen. What would you do? And so we look on the periodic table and we find calcium as a 2+. We look on the periodic table and we find that nitrogen is a 3-. And by the way, you can't have 2 pluses or 2 minuses. You got to have one of each. You got to have at least one of each. All right, and so I see this does not equal 0. 2 minus 3 is -1. And so I know we have to cross charges. So let's go ahead and push it together, though. Calcium nitride, more on naming later. And let's go ahead and cross those charges. Now remember, we are crossing just the number, not the positive part, because the charge goes on the upper right. The number goes down on the bottom right. Continue across. I need to continue across to the nitrogen. There we go. And now we're going to cross the 3, just the 3. And let's go all the way over to the calcium, Ca. And there it is, calcium nitride. And so bottom line is, if they're already equal, don't cross the charges, okay? So if I have aluminum 3+ and say, what should we use? And let's say phosphorus 3+, 3-, pardon me. They're already equal. So we don't want to cross the charges. And so we get aluminum phosphide. Now what would happen if you did cross the charges? Well, then we'd have this situation, which would still be, 0 for the total charge. The problem is we want these numbers to be the least or the lowest possible numbers. So the way to get at the least possible whole numbers is divide them all by 3. And we're back to the aluminum phosphide with subscripts 1. And by the way, we generally don't put a 1 and a 1 there. Okay, it's understood that you have at least one of them there. If you wrote it down, you have at least one. And if you put a number down there, usually it's not for the 1. So that's just a stylistic thing. So let's keep in mind now that the upper part over here, that this part over here is where the charge goes. This part down here is where the number goes. Number of atoms. That's where that goes. Okay? So we want to make sure that we're putting them in the right place. Okay?